Any questions at all about the homework? I gave you several that weren't in the book that only had answers. Yeah.
Question 541.
All right. Now.
I have a picture of it here.
This is a graph.
Yes.
All right. No, leave it that way. That way.
You like it this way?
Yeah, that's fine. All right. This one.
Yes, sir.
It starts at minus 12 dB, right?
Yes, sir. And then it goes down negative 12 dB a decade until it hits 3.
Here's 3?
3's on the frequency scale.
Yeah. All right.
And then it goes flat at 0 until 10 on the frequency scale. And then it goes down negative 20 after 10.
And they want something that does this, right?
They want the magnitude of the impedance sketched in the Bode plot.
Well, this is the magnitude, isn't it?
I'm sorry, that's given. Determine the one possible impedance expression for Z of P equals 0.8.
Yeah, and he uses P instead of S. I'm going to tell you that. This is Bode plot stuff. All right. So basically, when you do Bode, we might as well review this for everybody's benefit. All right. In general, Bode plot, it comes down to one thing. First, if you have any function that's made up, and I'm just going to do first order poles on this one. We can do higher order poles. If you have something where you have K, and then you have S minus A, S minus B, and then you have S, either can be plus or minus. It doesn't really matter at this point because the truth is you want the 0 happens where this is 0. Do you follow me in this class? When the quantity S plus B is 0. And then S plus C and S plus D. Now, when we have this as a function, I'm just going to call it f of s. This could be a z of s, where in general s is equal to some real value plus j omega. You remember that? That's complex plane stuff, right? Everybody remember this about s in the frequency domain being sigma plus j omega. So in a Bode plot, frankly, we don't care about sigma. This s is j omega. Follow me, everyone? Now, when we have this, the way you do a Bode, and there's probably there's variations on this, but I'm going to tell you the way I do it. I make sure that the coefficient of this is going to be 1. So I divide through the top and bottom by a. Can everybody? I'm going to pull a 1 over a out of here. Let me just show you simply. If I just had this function k times s plus a, I would make that k, and then what I'd do is pull a out of it, and I'd have s over a plus 1. Does everybody follow me on this? I want to get this to be something plus 1. Okay? Now, when I do that for this function, I'm going to have on top k. You don't have to do it this way, but it's the way that I do it. And I'm going to have a, and then I'm going to have b out in front. Then I'm going to have s over a plus 1 times s over b plus 1. And the bottom, I'm going to have c, and I'm going to have d. And then I'm going to have s over c plus 1 and s over d plus 1. Everybody follow me on this? That's the functional form. Now, with a Bode plot, the way you do this, got to remember the way the scale on this thing. This is common. Since we're doing, this is going to be voltage, current, or things related to voltage or current. This will be 20 times the log of the magnitude of whatever the function is. On here, it's going to be s, but really it's going to be j omega, because s is j omega. He uses p in that. In signals and systems, we use just s. We did not make s equal to j omega. Do you all remember this class when you did this? So when we're doing this thing now, my next step is to take 20. This is what I'm going to plot. I'm going to plot this function, which is 20 times the log of the magnitude of this. Now you'll notice what I get out in front. I get k times ab over cd. So first, I'll put them all down, then I'll break them out. It's going to be k times a times b over c times d. Then I have s over a plus 1 and S over B plus 1. Then I have S over C plus 1 and S over D plus 1 here. And now I break this out, and I'll write it up here. I'll get a different marker. Something else I'll tell you. In engineering, you use Bode plots for everything. Controls, electromagnetics, any kind of circuit design that involves frequent response, you're going to use Bode all the time. One key thing, remember, if it's power, it's 10 times the log of the function. If it's voltage or current related, it's 20 times the log. That's the one thing you keep your head on straight about, or else you will mess things up. So here, now what I'm going to plot, and I might as well just call it G of S, is going to be equal to 20 times the log. Now, you all agree that log A times log B is log A plus log B, right? So I break out the first term by itself. It's 20 times the log of K times A times B over C times D, plus 20 times the log of just S over A plus 1, magnitude of S over A plus 1, plus 20 times the log of magnitude of S over B plus 1. And then it's minus 20 because now I have these terms and they're 1 over something. Do y'all follow me on this, class? Just so everybody knows, if you have 20 times the log of the magnitude of 1 over S over, say, C plus 1, that's 20 times the log of 1 minus 20 times the log of magnitude of S over C plus 1. Do y'all follow me on this, class? It's minus that, right? Well, what is the log of 1? 0. So we just ignore that. That's what I'm doing over here. I'll get questioned about this usually. So it's minus 20 times the log here, and it's just going to be magnitude of S over C plus 1. And then minus 20 times the log of magnitude S over D plus 1. Now, I did this for a reason, because I gave you a function with both poles and zeros. And at this point, what you have to do is you have to show which order of magnitude or relative order of magnitude A, B, C, and D is. So if I say A is less than, say, B, no, let me go less than C, is less than B, is less than D. A could be 1, for instance. C could be 10, B could be 100, D could be 1,000. Follow me? On this axis over here, let me put this right here. On this axis, we actually plot the log of the frequency, log of F. So, but the paper, my old professors used to say, let the paper take the log, so you use logarithmic paper on here. So you have, like, whatever this is, this would be 1 order of magnitude, 2 orders of magnitude, 3 orders of magnitude, 4. And then you would get basically this. I think everybody knows what I'm doing here. I'm showing you the log being taken by the axis itself. Got me on that one? Here, it's just 20 times the log of the magnitude of G of S. But now we do that thing, we let S go to J omega. And here's the real magic of this. The only thing we care about is the point where S over A becomes 1. Then it's got the same value as 1 here, and that means because it's a J omega, well, if you have J1 plus 1, the magnitude of that is square root of 2. You're always looking for square root of 2 increases in the value inside those in the value inside the absolute values that I've shown there. Does everybody understand what I'm saying without too much detail about? You guys got this? All right, now, I've made this claim first. So A is the smallest value, all right? So down here, the first thing I'm going to put is an A. And then there's going to be a, what, C, right? And then there's going to be a B, and then a D. And obviously, this is not the neatest graph, but you get the idea, I hope. Everybody see this okay? You all understand why I'm doing what I'm doing? Now, first thing is, as you start, when S is 0, just listen to me now. Let S be 0, let omega be 0. That means you got log of 1 here, right? Log of 1 is 0. Log of 1 here, correct? 0. Log of 1 here is 0. Log of 1 there is 0. Everything's 0 except there. Got it? So that's where you start. Follow me? Here, you know you're going to start at, this point is going to be 20 times the log of the magnitude of KAB over CD. And really what I'm trying to say is it's going to be 20 times the log of all the constants after you strip them out from that S, all the functions. You want to always have S over something plus 1. Remember that. Always F over something. Sometimes people forget that. They leave it as S plus 1, and then they don't pull out those constants, so they get the wrong scale. That's what I'm trying to warn you against. Everybody okay on this? Remember to do what I'm showing you on this. So now this thing starts here, whatever that value is, right? It starts, as soon as it starts, it's going to stay at that value until I hit A. Do you follow me? It doesn't change until all of a sudden S over A equals 1 in magnitude. And S is J omega, right? So it's really omega over A equals 1. Let me plot not log of F, but log of omega. That way it'll be easier, because I'd have to divide by, I'd have to take the 2 pi into account here. I just want to plot just omega, okay? Now, when you do this here, right, I say that starts, and you see how it's a positive 20. So it starts going up at a rate of 20 dB per decade. All right, until it hits C. I said C was the next one. When it hits C, then it starts going down. Well, it was already going up. It means it gets canceled. It just stays at the value it's at. Does everybody hear me on this one? So it's going to stay at whatever value that C is at until it hits B. And then at B, I said that B was greater than C, so then it starts going up again as 20 dB per decade, right? Until it hits D, and what happens at D? Just stays flat. Now, that's what would happen in this order. But I can change the order. If I made A less than B, less than C, less than D, then it would start going up at 20 at A. Then it would start going up at 40 dB per decade at B. Do you all follow me on this? Then when it hits C, it would just reduce the slope to 20. And then when it hits D, it would get flat. Do you follow me on this? So that's the trend you got to pick up on. Now, when you construct, how many understand what I've shown you here? This is a very rough way of explaining it, but it hits all the important aspects of Bode plots that people mess up. Most of the time, they forget to do this. They forget to take the scale everything so it's plus 1. That's the biggest problem with Bode plots most people don't do. And did y'all have me? How many had me for signals and systems? You did these in signals and systems. Did Irwin make you do them in circuits or not?
The very end.
He did?
For a week.
All right, well, did you do them in any other class, like besides this class? You had controls already? Okay. If you had controls, Hung did this for you. John Hung, I'm sure, showed you how to do it this way. All right, good. You're familiar enough with it. Getting back to this problem that you told me about. So now, let me take care of all that. Now what we want to do is get or describe this with a function and then turn the function into components. And there's usually, anytime they ask for components that'll realize a function, there's an infinite number of solutions. But there's always ratioing that you can take a look at. So with this, that minus, first of all, do you all agree I've got one pole, right, that's going to be at, what's this frequency, 1?
1.
At 1. Do you all agree with that? Then I got another pole at 3, right? It starts increasing. I got another pole at 10, correct? Let's construct this. So in general, what I'm looking at is this. I have some f of s, and I'm going to call this s for now. And this is, well, I can call it z of s, I guess. Because he uses z there, so I'll call it z of s. But he uses p. I don't like p, I like s. That's what you were taught, right? Did anybody use P for anything? I've never found out where he got that in that book. All right, Z of S, and we start always putting a constant K. You always put a constant K out there. You know you're going to have some odd constant value you have to figure out. After that, you look at this. Well, it says it's coming in. It doesn't show the thing flat anywhere, does it? You follow me on this, class? It shows it coming in at 1, and it's going to be a what? A pole that's coming in. Theoretically, it's 0, so you divide this by S. Do you follow me? Next thing, you can see it flattens out at 3. So that means you have S plus 3 on top. That's where it's flattening. You all follow me on this? But then, it doesn't stay flat. At 10, it starts going down. So now I have S plus 10 here, right? And that's the last bit of information they give. Correct? This is your first bit. I'm trying to answer your question, but I want to do it with a Bode completely, regardless if he wants elements to fabricate it or not. Now you can get this thing in the form of the Bode plot. So you can get your K, and that's going to be equal to K, right? And I divide by, or excuse me, I take out the 3, and then I take out a 10 here, and then I'm left with on top S over 3 plus 1, and on the bottom I'm left with S over 10 plus 1, and I have an S too, right? And that's the function Z of S, correct? Now when I break that out and I do the Bode of that, I take 20 times the log of this function, magnitude of it. I'm going to take 20 of log of K times 3 over 10. And then it's going to be plus, or actually minus 20 times the log of magnitude of S, just S here. And then it's going to be plus 20 times log of magnitude of S over 3 plus 1. And then it's going to be minus 20 times the log of magnitude S over 10 plus 1. Do you all agree with that? I know I'm boring some of you, but I'm trying to do justice to everybody to make sure there's nothing you don't understand about this. There's no aspect of this you don't understand. Now here's the real secret to this. You don't worry about all that stuff over there, right here. You say that right there and this right here have to be equal to minus 12. Follow me? At S equals, or at J omega. And is that plotted with F or is it plotted with omega? All right, great, great. If it's plotted with omega, it's not a problem. So now what I do is put minus 12 over here, right, is equal to 20 times the log of magnitude K times 3 over 10. I'll break this apart in a second. Minus 20 times the log of 1. Anything unusual about that log 1? What is it?
0.
It's nice he's chosen 1 there. Yeah, he's made life really easy, so just get rid of that. Now, this part's even easier because I've got minus 12 there, right? And I expand this, and I say that's equal to 20 times the log of magnitude of 3/10. And then it's going to be plus 20 times the log of K. I want K. That's the only thing I'm doing here. So now I can say minus 12, hope you can see this, minus 12 minus 20 times the log of 3/10, that'll be a positive number, by the way, will be equal to 20 times the log of K. And I want to solve for K, so really you can see what I'm going to do is divide that by 20 and take it to the power 10. Do you all see this? Can somebody just give me this number right here that I'm circling? You all know what I'm doing, right?
Yeah.
Can anybody give me the number? Anybody confirm that? Anybody confirm that? I just want to make sure it's right. Because these two are equal 20 log of K, right? All these don't matter, do they? All right, good question. Just let me finish this thought here. He said, why don't these matter? Well, when S is 1, right? This is not 1, right? 1 over 3 is less than 1. You only worry about it when this quantity, S over whatever, has a magnitude of 1 or greater than that. Then this turns out. So all these are off. That's my point, except for the S. This term isn't. You have to include that. But it's nice he chose S as 1, because you ignore it anyway, which is nice. Anyway, what's this value? Minus 1.5. All right, that means I have to divide that by 20 and then take that to the 10th power to get k. So k should be equal to 10 right there to the minus 1.5 over 20. Whatever that number. Yeah.
So, at least for this one, since the number's negative 12, can't you just make the k for e over, or for k over 10 equal to 1/4? Since negative 12 would be a nice 1/4 ratio.
Well, you do minus 12 over 20 first, right? You're going to have to divide that by 20, right? If you're trying to get k? Or?
I mean, wouldn't negative 12 be equal to 1:4 ratio in terms of voltages?
I'm actually not sure about that, to be frank. I just give me this number for k, please.
It's 0.8.
0.8? All right, so k is equal to 0.8. Now we have our function. We can say z of s is equal to 0.8 times s plus 3 over s plus 10. Now, does he ask you to build components?
Nope.
Huh?
Not this one.
All right, but if he did, what do you know about components? This is the thing I wanted to show you. Well, the way to build this circuit, if you're allowed all the tools in your bag, is with an op-amp. An op-amp makes this trivial, all right? And I'll just show you something. Remember this. When you have an op-amp, I'm going to do it the standard inverting. Let's make it an ideal op-amp. And you have, write this down too, you have two functions. That's V out to ground, this is V in. Call this Z2 of S, Z1 of S, all right? This is the beautiful thing about this. When I take a look at this, I know V out over V in, which would be the transfer function H of S for this, correct? If we're just trying to realize a function, I know it's an impedance, and we could make this an equivalent impedance thing, but right now just follow me on this part because it's important. This output, if you remember, is minus this impedance, Z2 of S, over Z1 of S. Well, if I put that equal to this, 0.8, right, times S plus 3 on top, right, over S plus 10. All right? If I wanted to get that, I'll show you a couple of ways to do it. This is something I think everybody has seen before. When you have a resistor in parallel with a capacitor is fine. And you take a look at this and take a look at the impedance of these two, where you got R and C. You know the impedance of this one is going to be 1 over CS. So you know actually when we take a look at Z of S of this right here, that is equal to 1 over R plus SC. Does everybody agree with that? Right? It's 1 over the first impedance plus 1 over the second impedance. Do you all agree with that? Now, if you take this and multiply, because you want to get the right scale in this, I want S by itself, so I'm going to divide top and bottom by C. Right? And this is up to you. Y'all see right here, I could say that this 3 would be 1 over RC if I wanted to use this right here for the top function. Do you all agree with that? Follow me on that? All right. Now, for this function, I could put another one of these together with a different value of C. Do you all agree with that? I'm just showing you a way to assemble this. I'm not going to spend too much time with it. Do you all agree that this, see, remember the bottom one here, we're going to have equal to that. The top one I'm going to make equal to this. Are you with me on this? And again, I'm getting an H of S, not a Z of S. So I'm getting a transfer function to describe that, because most of the time when you're realizing these things, you're not using components by themselves. You're going to use an op-amp to realize a transfer function. Almost always. Just remember that. Didn't you do that with John Hung's class, Dr. Hung's Signals and Systems class? Did he have you build circuits to realize functions? Just stability work? That's what you were doing? Well, this is how you build basically this is how you build a circuit. You start with a transfer function, what you want, and then you select the components to create that function. And there's a lot of ways to do this. If you remember back, how many had me for Signals and Systems? Do you remember the two different methods of realization? They were labeled the first and second implicit methods, where we divided everything. It was more involved in this. Do y'all remember that? There's a lot of ways to create circuitry or create things, all right? This is just one of many. So here I can say this function I'm going to realize with this, and that constant 0.8 would give me the value for C. Down here I'm going to get this function right here. I've got an S squared times that. So really what I'm going to say is anytime I have an S squared involved in it, I know I have an RLC. I'm almost going to use up too much time here, but I can tell you this. If you have this, would be S times S plus 10. Just call this a Z of S, all right? Or call this an F of S right here, and you wanted to create that function. Just listen to me now. Well, one way to do it is to start by saying, I'll have a function where I have just S plus 10 here, all right? And then I'll feed that function into something, an op-amp that just has S. This won't, I hope I'm not stretching this too much. So here's what I'm going to get at. I'm going to stop right after this thought so you see what I'm doing. Because he didn't ask us to realize it, but you should be aware of how to realize this based on the functional forms. I know what that function was. If I wanted the second one, S times S plus 10, watch this. If we have this is one way to do it. Actually, I don't like using inductors, but I'm going to this time. This has an impedance of SL, right? Then we use an R here. I could put a C here, but I'm doing it this way for a reason. I want you to associate poles with inductors. Or I mean, I shouldn't say poles, single values of S with inductors. So this is the input. This is the output, right? V out over V in is H of S, the transfer function. And that would be equal to minus SL over R. Do you all see that right there? Now take this output and feed it into something that has a second resistor, R2. Feed that into an op-amp, ground that, and coming up here, here's your resistor, here's your capacitor. Call that R3, and C here, and then this would come down here, and this would be your output. Now, when you feed this output into here, it's just multiplying by that transfer function. Do you all see this? Well, this one's transfer function is going to be minus this impedance, which is minus 1 over R3 plus SC, right? Divided by R2. And now you have the exact form you want to realize this function right here. Do you follow me in this class? I'm going to stop right there. I'm just telling you, think in terms of operational amplifiers with R's and C's to build transfer functions that have multiple poles and stuff like that. It's very easy to do. That's my point about this. All right, what's the other one? Since he just wanted the transfer function, there wasn't much to do. What was the next one you wanted me to do? Yeah. 5.4.3. Is this a transfer function creating or? What's that? Sorry. For this one? All right. So it's flat to what point?
megahertz.
Minus 20?
Minus 20 down to 600 megahertz.
How many?
600 megahertz.
600. Wow.
That is in terms of F now. So
Yeah, that's all right.
up 20 dB to infinity.
All right, and so this is a resistor, right? He's,
It was 457,000.
but it's a resistor. 400 what?
4,700 ohms.
Well, that's this may be equivalent to 4,700 ohms, but this is where I don't like this. This should be 20 times the log of 4,700 ohms. Do you follow me? That's what it should be there. He gives you the raw value. He says that's what it's coming. Yes.
He also says there's a 1/8 watt carbon resistor.
Uh-huh.
Does that matter in this?
No, it's just we're going to use the standard model for resistor. All right, if you remember, standard model for resistor is what? Well, you start with the element itself, the resistor, right? That's R. That's given, 4,700, right? Then in parallel with that, you have some what? CX, something you don't want there, right? Then in series with that, you have some LX. It has to do with L, call it L sub L, L of the leads. And this is the actual impedance that you're looking at, right? Correct, class? Now, if you remember what I told you when we did this, I said that if you were to plot the actual, and let me do it over here, the impedance of that versus frequency, and this is going to be the log of the frequency in this axis, so remember this is log of F, actually, not F in this direction, and versus the 20 times the log of the magnitude of the impedance here for a resistor. Then what you get is something that looks like this. This right here is the resonant frequency. It's 1 over 2 pi times square root of LC, and that's L lead CX. This break frequency right here is 1 over 2 pi times simply R times C of X. Right? Do y'all remember me showing you this, guys? How many do? Please make sure. I see it. All right. I drew this out for you. I told you why it's the case. So you always start at this frequency right here. I know I've got R. I want C. So I can find out C because there's the break frequency. And I can say that here, 6 times 10 to the 6th would be equal to 1 over 2 pi times R, which is 4,700, right? Times CX, or I can say that CX here is 1 over 2 pi 4,700, and then it's going to be divided by 6 times 10 to the 6th. Can you give me that value? Do you all see what I'm doing? This is 2 pi times 4,700 times 6 times 10 to the 6th. Just give me the value. Okay. Now, does he have that? Is that the answer? Yes. It is? All right. Now, to get the inductance, it's pretty straightforward because there's your next frequency, right? And that was 600 megahertz, isn't it? So the only thing you would do is take, now it's really 600 megahertz is equal to 1 over 2 pi, 1 over 2 pi, and this is going to be square root of LC, L lead CX. Well, you can rearrange them yourself, but you'll know what I'm going to be doing. I'm going to take what? This, and if you will, no matter how you do this, I can take the square root of LC on this side, divide by 600 megahertz, so I have 1 over 2 pi 600 times 10 to the 6th, right? Then I have the square root of LC, so then I square everything. So take all this and square it. And then I divide by C, and that would be L of the lead. So if you take 1 over 2 pi times 600 times 10 to the 6th and square it, and then divide by the value of C, you're going to get L. And I hope this seems very obvious. I'm going through it simply because sometimes there's one little aspect of this you don't see. For instance, you don't remember this. All right, that's usually the problem. And it's usually the low frequency you don't remember, the low frequency. What is this value? Anyone? nanohenries. Is that what it is in the book? Okay. You see that? It's not hard to do these things. Is there some? But I think all the rest follow suit, don't they?
Yeah, everything else is.
I think it's fairly straightforward. All right. Those problems are good problems, though. And what I'm going to tell you, I think I'm going to give this to you tonight. I'm going to give you a graph. Now, remember what I told you. These things are approximate, not exact, right? And based on these graphs, I'm going to ask you to extract values. If it's an inductor, capacitor, resistor, the values of the parasitic stuff, all right? It shouldn't be hard to do, I don't think. But at least you'll have a real graph that you have to kind of work with. Because in the real world, one of the things that frustrated me to no end was when I was taught about concepts, they never said what the error bars would be or how accurate those models would be. They just say, here's a model we use, and then you get some raw data and you try to fit the model, and you realize that that model was based on a lot of assumptions that may not be true. And I'm telling you that, especially when modeling inductors at high frequency. I'm warning you, those are a nightmare because they don't look anything like that you think they should. All right. So today, I'm going to go ahead and just mention grounds. I don't test you on grounds, but electrical engineers and electrical and computer engineers have to know about grounds. Has anybody had a formal course in grounding here? Anybody electrician in this room? You're an electrician, certified electrician? Then you could teach this, right? Because he's actually been taught the electrical codes, right? The first thing that usually you're shown is what's called and this is a simple signal ground, and it looks like this. This is a signal ground. All right, and this is all about grounds, electrical grounds. Well, a signal ground is something that's used on like a breadboard or on a small little, I'd call it a piece of something like FR4 or Doroid board. This is placed within an outer housing. The outer housing is a chassis. You all see these metal boxes that they use? Those are chassis. This is a signal ground used at that point. The next is something called a chassis ground. Chassis ground has this symbol. A chassis ground is for, like if you have a cabinet or something like this, and you're going to have boxes that are in there. They're basically metal boxes that have a bunch of wiring and chips and stuff inside them. Chassis grounds are inside of metal containers like this. This is a chassis ground right here. And you may have a component there, maybe a board there. And these would have effectively, on each one of these, they would have signal grounds, and the signal grounds would be connected to the chassis ground. Now, the chassis ground is something you got to be aware of for one reason. When you're doing measurements of signals that are 100 kilohertz or higher, anything like that, or clock cycles, if I go and I use this ground, and I start measuring voltages on this chip, I may get an error because this will develop an impedance. And that impedance will cause a voltage difference that you don't want. If you're going to get grounds, measurements, accurate measurements on individual boards inside a chassis, you've got to put your negative lead on the ground on that board and then do the measurements. All right, do you hear me on this one? All right, because it's very convenient to like tab this thing with some kind of a, like an alligator clip, and then go take your probe and start measuring voltages there. But the problem is this, if it has a long lead, this will develop a voltage that will cause your readings to be off by that voltage. So you always want to get your ground on the board you're measuring, as close to it. That's the first thing. Now, so this is a chassis ground. I'm going to tell you other warnings about this. In cabinets especially, where you get a bunch of different chassis stuck in a metal box and stuff like this, then you can get all sorts of weird effects for the high frequencies. And you can get parasitic capacitances causing problems. We'll get into ground loops. But you've got to be careful when you do measurements to keep the leads as close as possible to the points where you want to measure. And always make sure if you're going to use a single ground, it's on the board you're trying to measure, the smallest, or the actual like FR4 board or something like that. Don't put it to the bottom of the chassis. Now, the earth ground is the one I don't have a lot of expertise in, but I can tell you this from lightning work. I know enough. When they talk about an earth ground, the symbol for an earth ground is this. It's a triangle like that. What it really is supposed to be is if you go to Lowe's or Home Depot or Ace Hardware, you're going to get something kind of called a grounding rod. Are they 7 foot or 8 foot? I forgot the. I mean, it's a standard grounding rod. It's about that tall. You buy it, it's solid, it's steel. All right, and I don't know what diameter is, but it's fairly thick. It's hard to bend. Now, that grounding rod is supposed to be pounded into the ground, and I think that what they tell you to do is you're supposed to put water, and I don't know if they allow copper sulfate or what they allow around it, but what do you put on? They put it on there because copper sulfate's a very good conductor. It'll make this thing have a very low resistance to the, you might say, the outside world, the earth around it. And you pound it in, get it down there. And I don't know the gauge wire in Alabama that you're supposed to, the thickest gauge, 2 gauge. The thicker the better. And what that does is it assures that any signal where there's a fault in your house, it'll short. This is going to come internal from the power company. If it's shorted to that, it goes right to the ground and it doesn't route somewhere in your house and start a fire and things like this. The other thing about a grounding rod is so important. If you have any type of basic lightning protection, like if you up at the roof, if you have anything that's going to be a strike for lightning, a high point, then that goes right to the actual earth ground and avoids your house from getting burned up. I should tell you one story very quickly about something that happened. I don't think I've told you about a kid I taught who I went to his house, and a phone call. It was in the summertime, and we had just covered the importance of grounding and how if you don't do that, if you get struck by lightning, your house could burn down. This is a true story. Did I mention this in this class yet? It's an absolute truth. So his name is Paul Rod, and he's working at, I think it's for the Naval Surface Warfare Center down at Pensacola. He's doing great work, and he's involved with some classified sonar work that he can't tell me about other than it's towed arrays, and that's all I can tell you. Anyway, what happened is this. We're teaching about this, and I said, if you don't use a ground when you have a house, a proper ground, and this is your house, well, when lightning hits your house, if this is lightning, right, it wants to get to earth ground, and it goes through the path of least impedance, which may be some electrical wiring. It might be a cable, like for cable TV. It's anyway. Lightning has a fairly high current magnitude. It gets up to about 270 kiloamps, usually 20 to 50 kiloamps. So it comes down here, and it's looking for a way to ground and stuff like this, but if it doesn't have an obviously low impedance path, it'll take the path, what it sees as low impedance, and it'll start fires all over. That's the way fires are started. Well, his father, this is the ironic thing, works for the power company. And there were strikes around his house that have taken out trees already. This is his dream home. He's just built this thing. And it's on the top of a rather rocky area, so which means the soil doesn't have a lot of, it's not very conducting. And this guy had purchased equipment to make your home safe. The only thing you need to do is go up about, if your house is 50 foot tall, you go about 20 foot beyond that, and you just hang a thick gauge wire right over the roof. It's called a cone of protection. You got to make it extend a little, like that, and just take that and take it right down to 2 grounding rods. That's all you need, and you're protected. And he knew that, but he didn't do it. He had the equipment to do it. So in the middle of a class, just after class, go up to my office, and I get a call. My dad's house is on fire. It got struck by lightning. Are you kidding me? And it's true. And he could tell in his voice he was serious. I went out there, and sure enough, lightning had hit. Not just hit, but the way it got down to ground is it jumped into the rebar on the concrete. He had a sloped driveway, and the concrete was blown up. Right? So this is a heavy lightning hit. All right? Pieces of chunks of So in the midst of the fire, the best part of the story was we're there, and we're talking. The police are there, fire trucks and stuff like this. We hear bang, 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 bang. He had a giant bunch of munitions. He had like odd 6 shells, 22 shotgun shells. You want to see people running? This stuff was going off, but you could hear it pinging around you. So it was, and man, I've never seen that many people move that quick down a muddy hill, just sliding. That's a true story, too. I'll not forget that part of it. Moral of the story is grounding's important, and especially with houses. I mean, I've never messed with this myself on a house. I've had to deal with high power. I had to deal with huge currents with the railgun. I learned to be nervous about everything. I wanted to go make overkill that I didn't get myself killed in terms of safety. And anything that needed a ground got a ground, and more than one. All right, now that's the real truth about grounding. And Whitmer's book has a couple little things about problems. The truth is you want to make your ground connections to the ground as short as possible, and you never want to have more than one. And let me just give you an example. If you have something like this, that's some product, and this is effectively ground, you don't want to ground it here and here. You only want 1 point. And the reason is this. If you get 2 points, then this becomes, there's several things. This becomes a loop for starters. So if you have time-varying magnetic fields in there, you induce currents in here. That's the first reason. The second reason is when you have 2 points, if currents, heavy currents like lightning hits here, then some of that current can shut right through there. You follow me? If you have more than one connection. When you make ground connections with anything, only one ground connection, unless it's lightning protection, you can take 2 to the ground then, all right, on opposite ends. But when it has to do with anything else, it can be ground only at 1 point, and try to make it the shortest possible ground connection. In other words, if you have product like this, and this is your ground, don't have it like this. All right. Have it straight down, shortest possible distance that's feasible. And grounds become very important at high frequencies when you're doing any high frequency work, effective grounds. That's it with grounds. I know I'm about out of time, but I'm going to mention one other thing. I'm going to tell you on Friday, I'm going to go through a rather detailed discussion of any type of clock circuit and the EMC around it. This is important. You're here for Friday's lecture. But with shields, I'll go through a bit of it right now. Look, I'm not going to test you on grounds, but I want you to be aware of grounds because you're electrical engineers and you're going to have to work with this. And remember, most of the time, if you're working with a ground, like with a radar unit or something like this, there's electrical codes that dictate what you need to do. Like electricians like him or you, if get an electrician to help you if you have any questions, if you're going to ad hoc something for a small company, because you can really get in trouble if you don't, especially with high power stuff. You got to be very careful with that. But anyway, getting back to the shields business. Electrical shielding means you want to prevent a signal from either getting out or a signal getting into an area. That's what a shield is. The easiest possible shield you can get is a piece of good conducting material that's fairly thin. So we start with a planar shield. We'll get to the actual shields that are wrapped around there. But normally a shield would look like this. It's a certain thickness, and it's usually got a very good conductivity. It's got a thickness D. And assume it's got a high conductivity, it's got some mu relative, and it's got some value of epsilon relative, but these are usually they're trivial, you don't need that. So the way Wentworth's book does, he assumes I have an electric field coming in normally incident. Now there's only three things really you have to worry about. First is how much gets in here. So they want the transmission coefficient at that interface, which means they need the characteristic impedance of free space. Then this shield is going to have some N shield, right? It's going to have N shield would be equal to the square root of J omega mu over sigma plus J omega epsilon. Almost always, this is simply the square root of J omega mu over sigma. The omega epsilon is usually of no consequence. Got me on that, everyone? Now, the other thing is, this shield impedance is usually much, much less than eta naught. Eta naught's 120 pi. So I get this right here, tau 1, would be equal to 1 plus the reflection coefficient, and that equals 2 times eta shield over eta shield plus eta naught. Normally, you ignore the eta shield down here. It's just 2 times eta shield over eta naught. That's the transmission coefficient. Got me? I'll be done in 1 second. Clear on that, class? Once it gets in here, Wentworth's book has it looking like this. It decays rapidly. So in here, it's going to decay at a rate e to the minus alpha, all right, times the thickness d. from here to here, that's how much decay it undergoes. You don't worry about the phase ever. Does that make sense to everybody? All right, so I'll take this, and then I'll multiply it by this. This is going to be the total decay. I'll have e to the minus alpha d, and alpha, of course, is going to be the real part of j omega, square root of j omega mu times sigma plus j omega epsilon. It really, I'll get to that next time, but it's going to be a value that is significantly large. It's fairly large. Just trust me on this one. So I have this, and I have 2 eta shield over eta shield plus eta naught. That's tau 1. And then when it gets out of here, if you just listen to me here, there's going to be a transmission coefficient tau 2. Now this is the interesting part. Please listen to this. When I look at this tau 2, well, it's twice the impedance I'm going into. I'm going into free space. So it's 2 times eta naught over eta naught plus eta shield. Well, hear me now. If eta shield is much less than eta naught, it's about 2. You all see that? With me on this? I know I'm over, but just bear with me. So then if I multiply this by 2, now I have the ratio of E transmitted over E incident magnitude. And from there, I can take 20 times the log of that, and I can get the shielding effectiveness. I'll give you a little reading and give you some problems on that. You're going to send me a message, what's the quiz on? And I could say on paper, but it's going to be involving capacitors, inductors, and resistors. Okay?